Somebody staple papers like by folding them. No, it's like someone cut it weird and like tossed into it. It's like a staple. Cut it weird. Yeah, weird.
Pretty sure. I actually had it like.
Oh yeah, long list. Yeah, I just had the negatives and the positives both came out to the same number, so 192 equals 192. I completely forgot what the homework I had done last started. Then it probably has an active timer running on the quizzes page. When it reaches 0, it'll refresh the page and lock you out.
See, I feel like as long as you start,
If you want to test that, really, go
I
right
don't want to test it, but I feel like as long as you start it before
I don't think that's how it works.
you're good.
I don't think it would be good.
You know what I do? I started in 16, and then you see it there, lots of, like, I'll do it, I'll put it.
All right, good afternoon, everybody. So
Just do it like before the time.
today we're going to continue on with lecture stuff. Remember that you have your first quiz, which I'm trying the online thing. So log on to Canvas. Hopefully, if you could log on to Canvas some point during the afternoon, just to make sure the class shows up for you. That way, there's no problems on that end. And then the quiz, I think, opens up at 5, and it goes till midnight. Okay, so you have 45 minutes to complete it. Once you start, the 45-minute clock starts going. You're allowed to use any materials you want. Just you can't do it in groups. So please respect the academic integrity policy. And yeah, I don't think it's going to give you a grade. I think it'll give you a grade right away, but it won't give you the answers to the questions, because then that would be unfair to people who took it later on, or earlier on in the day. So are there any homework questions? So I will be collecting, actually I want to wait until after the quiz is done before I collect your homework. So I'll collect homework number 1, I'm going to push it back till Monday. That way you have the homework in front of you while you're doing the quiz. So are there any homework questions though? Specific? Yes.
Number 35, at the end, when you're solving for ISO.
Yeah, let me bring it back that way I can. And also, I got some questions before I'm going to get to your issue. I had some questions about the homework in general. So, do I have all the materials I need to have up on the website in terms of being able to do the homework from the correct version? So, okay, so essentially, the best way to go about this, because someone was asking, what version of the book and all this other stuff. So inside the homework solutions themselves are the problems. So if you didn't already know, from this point on, right, these are the homework assignments. Okay, the numbers that you're going to do, and then simply you use the version of the question that's available in the solution. So you have everything that you need in order to do the homework, even if you don't have the book in front of you. okay? And I believe that these are probably from the older version of the textbook, but I don't see any reason to change the homework problems. They're fine the way they are. So is that clear to everybody, just from this point moving forward? Now, your homework question.
So 35.
Got it. Okay, so, better make it smaller. It's not. All right. The question asks us to find Ix in the network here. So, really, using KCL, I mean, that's not the way that it asks you. It doesn't specify. But using KCL, you should be able to tell right off the bat what it is, right? I mean, eyeballing it, you can see that if we apply KCL to that middle top node, there's 2 amps heading out, which means, so there's 4 amps heading out, so there should be 4 amps heading in. So I'm assuming, hopefully, that the answer that it provides is 4 amps. Now, in Chapter 1, we haven't, I guess, explicitly learned KCL yet, and in most of these problems, they ask you to use Telegin's theorem. That's what they were assuming that you would use. So let's go through and let's apply Telegin's theorem. So we can see here, first thing, which of these elements obey the passive sign convention and which ones don't. So this one does not, this one does, this one does, this one does not, this one does. So essentially, all of the sources do not obey passive sign convention, and then all of the, I'm assuming, are passive elements, they do. So what we got to do is we know that the power consumed of all these added up should equal 0. And the way that we can use that to find Ix is because the power consumed by these two, am I being too broad in my answer? Do you have a specific question about one part?
It's just, how do you plug it all in?
Sure, we'll get to that point. Okay. So, right, where Ix comes into play is that Ix, you won't be able to find out the explicit power being consumed by either one of these elements, because it'll be dependent on Ix. So you add these up to 0, and then you'll have your Ix left over as the unknown. So the first thing that they do is they go through and they calculate the power consumed by each one of the elements. So this one is negative 36 volts times Ix, because, again, it does not obey the passive sign convention, so you flip the sign. P1 is 12 times Ix, because it does. This one is 48, which is 2 times 24. This one up here, okay, so here's what makes it a little bit more interesting. I didn't see this. This is a dependent source. So when you multiply, or when you calculate this one, okay, for the dependent source, right, you have a current going like this, 2 amps, and the voltage is Ix. So the power being consumed by this element, dependent source, is going to be equal to, and what I'll do to make this a little bit easier is I'll define another current which obeys the passive sign convention, right? So I'm going to call this IDS, and this is equal to VDS, right? Because this is the voltage across the dependent source. This is the current through the dependent source obeying the passive sign convention. So we know this will be VDS times IDS, which gives us Ix times negative 2 amps, which is negative 2 Ix. So that is a little bit of a loop, but when you get elements like this, sometimes it's easier to break it down and make sure you're just applying the passive sign convention the correct way. So hopefully that's what they have here. Negative 2 Ix. And then the last one will be easy. This will be 2 times 28, which gives us 56. So now all we have to do is add all of these two together. And so what we'll end up with is, first I'm going to add up all the ones with Ix's in them. So it'll be negative 36 Ix plus 12 Ix minus 2 Ix, and then 48 and plus 56. equals 0. So that's what they have here. This equation, again, actually that equation is not right the way they have that defined, because they move things to the other side. That should be, yeah. Is that what your question was?
Yeah, that's
Yeah,
right.
that equation's wrong. Because the way they have it defined, all of these are in terms of power consumed. Which means that the equation should actually be P30, well, I switched to using their notation now. P36V plus P1IX plus P1 plus P2 plus P3 equals 0. Okay. So let's go ahead and solve it like that then. So this right here is the same as what I've written, where this is the P36V, this is the P1X, this is the P1, P2, P3. Okay, so let's solve this. So what we're going to end up with is, when you add all the IX's together, you're going to get negative 36 plus 12, which will give us negative 24, minus 2, which is negative 26. So you have negative 26 IX. Hopefully it's giving me the right number. Plus 48 plus 56. So that's going to be, so 64, 104. I'm doing this all in my head, so hopefully this is right. Then we can move this to the other side, so we'll have 104 divided by 26 equals IX, which is 4 amps. Yes?
I think they're implying that all the powers are positive, so they just moved P36V and then P1IX over to the left side.
Yeah, you're right. That is what they're implying, but that's, I would say mathematically that's wrong. You're right. That's exactly the assumption they made. What they did was they switched it, where they originally defined P36V as the power being consumed, and then they say, oh, this is the power being injected now. They should, to be mathematically correct, have changed the variable name, because when they define it above, that would lead you to believe that that's still the same consumed power. But yeah, that's exactly what they were thinking. Anyway, so I recommend that you don't do what they do. Don't switch your variable name. Because as you can see, if you would have switched the variable name and still used the negative, then you would have ended up with a different variable name. So rely on the math. Translate the circuit to the math. And then once you're in that math realm, really, really adhere to all the signs and the variable names, and don't try to dig into it. Any questions on that one? Yes.
So in this case with P36V and P1IX, they would be supplying or anything else?
Yes. Right. Which elements were those? P36X? So this one is, oh, they're both the sources, which makes sense. Yeah, the two sources are supplying. And you can tell, actually, all the rest of them are consuming because of the direction of the current here, the direction of the current here, and the direction of the current here with the knowledge that IX is going to end up being positive. So it's pretty easy to, when you look at the picture, to pick out which ones will be consuming and which ones will be supplying. These, just to give you a quick note, they imply that the 1, 2, and 3 elements will be consuming, that they're loads, but they don't explicitly ever say that. So I don't think you could end up with a quiz problem that was similar to this, where 1, 2, or 3 was supplying, and that wouldn't necessarily be wrong, because they just tell you 1, 2, and 3 is something you don't know what it is. So I guess it could be a source on the inside. Any other questions on homework number 1? I think most of these problems are pretty similar to this one. The dependent source is probably the big loop, the big question mark. And this, I will, let me make a note to myself to try to clean that up. Okay. So, all right, so where did we leave off last time? Yes?
Real quick, Larry.
Sure.
I am on Canvas, and I don't see class on Canvas.
Okay, so let's get that cleared up now, actually, because I don't want there to be any problems. Let me mute this for a second. I'm going to log on to Canvas and make sure that everything is published in the correct way, so there's no problems tonight. So leave your computer up. Let me do this. Sometimes you can think that you've published something. All right, try it again. Okay, good. I just because I hit that button one more time. Okay, so good thing we checked out. All right, where did we stop last time?
Sample 2.5.
Sample 2.5? All right, great. So before we get to that stuff, let's talk about a couple things that we discussed last time. We've already gone over KVL and KCL a couple times. I don't think there's any reason to ask questions about that, right? These are the two basic laws that we're going to be using to solve that, coupled with Ohm's law to solve most of the problems before we get to chapter 3 and chapter 4 when we get to nodal and mesh analysis. Last time we talked about one type of circuit structure, which was the voltage divider. Can anybody remind me what that does? Yes.
It takes some V in and changes it to reduce the out using two resistors. The V out would be parallel or basically across the segment.
Exactly, right? So what we have is source, we have what we normally call an R1 and R2, okay, and we have an output. And what we saw was that we can use this equation to build a circuit that allows us to attenuate voltage, right? We can't, using this, the ratio of R2 over R1 plus R2 can never be greater than 1, so we can't boost it. There was one assumption, though, that was required for this thing to work. So let's imagine that there's a load over here. Okay. And actually I'm going to draw one other thing. Okay, that's the current going into the load. So for this circuit to operate ideally, and this is the ideal expression over here, what should this be? Yes, 0, exactly. The voltage divider ideal expression assumes that the load is drawing no current from the voltage divider, because this expression is derived from this circuit without any resistance in parallel with R2. If you remember, we went through an example where we showed how that would change, because when we have an RL, then we actually have to build our voltage divider expression using a non-ideal version, which would be that, okay, where RL is in parallel with R2. So if this is what you're trying to get, this is what you actually get. Now, when do these two expressions become the same? Okay, that has a lot to do with how we combine resistors in parallel. So when we combine resistors in parallel, this is another thing we talked about last time. First rule is that you always end up with a value that's smaller than the smallest of the two resistors. So if you're combining a 1 ohm resistor and a 1 million ohm resistor, the parallel result is going to be less than 1. Now, the combination between a resistor and an infinitely high resistance, okay, gives you the same resistance back. So the higher this other resistor is, the closer the parallel combo is going to be to R2, right? Let's say this is 100 and 100, your answer is 50. If this is 100 and 100 million, your answer is going to be pretty close to 100. So what we saw was that in order for this expression to look like this expression, RL needs to be a large value. And we set a threshold, which again is just a rule of thumb. It would depend on what design you're working on. Does anybody remember what that threshold was? For the difference between RL and R2, where we could assume that it was
Double. If it's more than double, then
close. There was a number 2. It wasn't double, it was 2 orders of magnitude. So instead of times 2, times 10 to the 2. So if you have 100, then 10,000. I wouldn't get so much caught up in the 10 to the 2 part, just understanding that RL has got to be a lot larger than 2. So we also talked about series combination of resistors. And so yeah, I'm going to move it down. Thank you, though. Do keep saying that, because sometimes I won't write a lot of junk and not figure it out. Okay, so let's take a look at these 3 circuits. The rule that we had for resistors or any elements to be in series with one another is that they have to share one node, okay, and there has to be no other branches that are adjacent to that node. So this is a no-brainer, the first one. Obviously, these 2 resistors are in series with one another. So what we could do, if I call this R1 and R2, we could replace this with a single resistor that is R1 plus R2. Now, over here, do we have any resistors that are in series? No. Okay. R1 and R2 are not, because although they share a node, there's another branch that's adjacent to that node. And R2 and R3 are actually in parallel. because they share both of those. What about over here?
So, does that mean that R1 and R2 are also in parallel?
No, they're not. Because for parallel, so for series, they share one node, no other branches. For parallel, they must share both nodes. And so these two share this, and they share that. These two only share one. These two nodes are not the same because of the source right here.
So is there like a way to
No.
say that they're not in series with the...
Yeah, there's series and parallel are special cases, and not all resistors are going to be either. You know, so they're not anything. They're just different elements inside of the circuit. Now, if I were to make that source 0 volts, then all of a sudden now they're in parallel again, because remember that, give me 1 second. Remember that our definition of a branch, it means it has to have more than a 0 volt difference, or a non-0 volt difference across it, which then would make these two nodes electrically the same, and then we'll put them back in parallel. Yes?
I was going to say, could you combine R2 and R3 in parallel and then combine the other one in series?
You could. See, and actually that's forward thinking, because that's the type of stuff we're going to get to later on in this class. That is going to be the way that we are going to simplify circuits. Because you can say that R1 is in series with the parallel combination of R2 and R3. So if you wanted to come up with an equivalent resistance that satisfied or that represented all three, it would be this: R1 plus R2, R3. Okay? And so then that would allow you to solve for the current, and then you could go and move backward. So, now, down here, do we have any resistors that are in series? We do, right?
R1 and R2.
R1 and R2. And we also have R3 and R4 that are in parallel. So we can sum these two together and say this is R1 plus R2. These together and say this is R3 and R4. And then we could say the whole resistance is R1 plus R2 plus R3 in parallel with R4. So that's something to get used to, is how we treat parallel series resistances, how to pick them out. And also understanding that not every set of two resistors is necessarily going to fall into one of those categories. All right, now let's get to some notes. So it was 2-5 you were on?
Yeah.
All right. Are you sure it wasn't 215? Maybe I wrote something down wrong in my notes. Because we did, I'll switch over to the screen. Because we did this where we combined multiple resistors and multiple sources together. I think this is the next one that we have to do. We talked about resolution. I guess the question is, did we do this circuit right here?
Yeah.
We did, right? Okay. So I must have said 2.5, but it's really 2.15. Okay. So, example 215 asks us to solve this circuit here. The mouse is moving up. There we go. Okay. So the first thing we're going to do here, like usual, is we're going to label everything. So we have our voltage, which we call V1, our voltage V2, our voltage V3, and all these are set up to try to obey the passive sign convention. Okay, I'll call that I loop. Now, you can see that there's multiple ways to solve these problems. Okay. One way would be applying KVL. Another way would be to simplify the circuit and use Ohm's law. Right? Because we have a single loop, we should be able to combine all the sources and resistors together, and then what we would be left with is a single voltage and a single resistor. So why don't we try the second way just for the heck of it? And since we've done the other way a couple times, we'll try that. So that means that step 2 is going to be to redraw the simplified circuit. Now the way that we're doing it here doesn't make much sense for this circuit, because again you could just use KVL. But when we get to more complex circuits where we have multiple branches and all this other type of stuff, this is going to be the process that you're going to have to use. So order doesn't matter, because remember we saw that when we wrote out the equation in KVL, we saw, right, for additivity, order is irrelevant. So I know that this is going to be a single source combined with a single resistor. Okay, what is the resistor going to be? The resistor is going to be the series combination of all three of those together. So R equivalent will be equal to 10K plus 20K plus 30K, which is V equivalent. And here we have to be careful with polarity. So if we're going to assume that IL still goes in this direction, that means that the polarity of this source matches the polarity of the 6 volt. And that has an effect on how we add these things together, because you could do 6 minus 12 or 12 minus 6. IL still rotating clockwise, so that means that it's going to be 6 minus 12 volts. Does that make sense to everybody? So our V equivalent is going to be negative 6 volts. Alright, and so now we just got to solve this for IL. use my calculator, I'm pretty sure that's 1 million. 10 million. I'm not good at doing math in my head, I'll be honest. Alright, 6 divided by 60. 0.1. Negative 0.1. Okay. Now, and I'm almost off the screen. So now, what's one problem we have with solving this? Okay, note that because we simplify, we lost some resolution. We used that term last time. And can no longer solve for V1 through V3 directly from the circuit. And when I say this circuit, I mean that circuit. Because V1, V2, and V3 don't show up anywhere in that. What we can do, however, is we can use Ohm's law. I should be able to squeeze that into the bottom. Step number 4 is use Ohm's law to solve. Okay, and so we know that V1 will be equal to 10,000 times IL. So that will be 10K times negative 0.1 milliamps, which gives us negative 1 volts. Yeah, I could read that in my head. Yeah, negative 1 volts. Okay, V2 is going to be, well, actually, they're just double and triple. So you should be able to just negative 2 volts. And V3 is equal to negative 3 volts. And you can already see that there's some congruency between here and down here. Because what do we expect for the loop? The voltage in the loop should sum together to be 0. And so the polarity of V1, V2, and V3 oppose the polarity of the source that we defined. So that means that it's really a negative 6 minus a negative 6, which is this. So we could say, step 5, use KVL to verify your answer. And going back to the original picture, that would give us 6 volts minus 12 volts minus the sum of V1 plus V2 plus V3. This is negative 6 volts. This is negative 6 volts. And so, right, you end up with 0. So that works. And that's just a basic example of how we can use simplification to solve circuits. In a different way, it ends up with the same result, it's different than how we would do it using the KVL. All right, next topic. And if there's any questions on anything, obviously you can always just call it up. All right, section 2.4. is single node pair circuits. So we already did we just did single loop circuits, right? That's mostly what we, the last 3/4 of the class or so, we've been working on circuits where there's just a single loop. And single loop circuits are one of the easier ones to solve because you have this common denominator, which is the current, is the same through all the elements. For a single node pair, it's going to be sort of the same thing, except now the common denominator is going to be the same voltage across all the devices. And whereas here, we were looking to see what the different voltage across the components were. With this new case, we're going to be looking to see what the different currents through all the components are. So a single node pair looks like this. All right, you can have a voltage, you don't necessarily have to, I guess it could be a current. And then you have a resistor, another resistor, and let's say we can also throw in a current source. Okay, so we'll call this BS, we'll call this R1, we'll call this R2, and we'll call this IL. So the reason why this is a single node pair is because how many nodes do we have here? Two. We have node number 1, node number 2. And because there's no branch in between any of these points, right? They're all at the same potential. We can say that they're the same node. And because they're the same node, now we automatically know that the voltage potential across R1, R2, and IL all equal Vs. So now what we're going to be looking for to solve is what is I1, what is I2, what is IS. So for single loop circuits, we know that there's only one current in that circuit, and we're solving for the individual voltages. For the single node pair, we know there's only one voltage, and we're solving for the individual currents. Just like we talked about parallel and series, not all circuits fall into one category or the other. Okay? Some resistors are neither in parallel or series, and some circuits are neither going to be a single loop or a single node pair. Our strategy in this chapter is going to be to try to make circuits look like one of these two using simplification. All right. And I'll add real small down there via KVL and via KCL. So KVL was the law that we were using predominantly to solve the single loop circuits. KCL is going to be what we're predominantly using to solve the single loop. All right. So there's certain parts of these notes that I don't think are that important, and I want to figure out what I want anything out. Okay. So, the next question we're going to ask ourselves is, what is a current divider? So it's a lot like voltage divider, except it does the same thing with currents. It's a It's a circuit that allows us to attenuate a current as needed, just like a voltage divider was a circuit that allowed us to attenuate a voltage. So let's say that we have space a little bit tight, but I can put it in here. So this is our source current. This is our R1. This is our R2. And just like how with the voltage divider, we had to pick the voltage that we quote unquote consider to be the output, right? We have to pick the current that we're going to consider to be the output here. So we're going to assume that this I so the current across that secondary resistor is going to be the one that we're trying to control. And actually, let's call it I2. I2 is the output. So we're going to come up with an expression that relates I2 to IX. And what's that expression? Expression looks like this. So you can see that the structure of the equation is pretty similar to the voltage divider, right? The main difference is now it's the opposite resistor up top. Right, if you remember, right, for the voltage divider, it's the resistor that we are considering through the load resistor that's in the numerator, right? That's the voltage that we're considering the voltage across that one. For the current divider, if we're looking at the current through R2 as our output, then you put R1 into it. And so how would we solve for this? So if we take the circuit, I'm just redrawing what we already had. And we're concerned with IL, or I2. So how could we write an expression that that represents this? If you go back to this table here, remember, so this is a single node pair, which means that we're going to solve for current via KCL. So we're going to apply KCL to this. So we know, and I'll give this a name as well. I1. So we know that IS is equal to I1 plus I2. But we're trying to get an expression that's going to be in terms of the resistance. So how can we do that? Not too many options at this point. We're still in the beginning of the class, so I can pretty much make this like a multiple choice question, right? Just like 4 choices that we got. So you can probably just take your chances of just throwing out one. Not KVL, right? Ohm's law. Okay. So we're going to use for that Ohm's law. All right, so let's define Ohm's law. Define Ohm's law for these elements. Now I know that it may seem like we're going through these problems really slowly, or maybe for some of you it doesn't, but this sort of methodology is what is being able to apply to the simple problems is what's going to help when you get to the circuits that look like. Circuits that look like that. Because being able to, it's really all about applying those basic steps in repetition over and over again. The problems, at least until chapter 3 or chapter 4, don't necessarily get harder, they just get longer. Okay, so for IS, or actually, and one thing I didn't do, which is I did not label everything, so I'm going to put in here step number 0, label everything. And so we know that there's only one voltage here. We've labeled all the currents already. So all I really have to say is that for this whole circuit, and that's what the dotted line means, we're calling this V node pair plus and minus. So can we define Ohm's law for the current source? Right, you can't. That doesn't work like that. So, can we do it for the first resistor? Yes, we can. And so what we'll see is that I1 is equal to V node pair over R1. And we're going to do the same thing for R2, which tells us that I2 is equal to V node pair divided by R2. And so now we can substitute these back in. So we make our substitutions, and what we end up with is 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 equal to V node pair times 1 over R1 plus 1 over R2. So not exactly.
I thought so.
Siri, I guess I put my thing on it, so it was listening to my whole thing, and then it was like, great. Thank you. Siri said I'm right, so I guess that must mean something. Okay. All right. So where do we stand here? And this is where there's so many different ways to solve this problem. So I'm just going to route through the next steps. We know again that we need to get an I2 back in here, right? If we want to get, the thing is, this is really now just math. We're trying to get this into the proper form. So I think the rest of this we can just kind of do it all as one step. So we have. And getting equations to fit certain forms is a skill that you have to learn over time. And I'm not really going to ask you to do derivations, so this is more for just demonstration than anything else. All right, so we know that the V node pair, this may seem a little bit counterintuitive because we're kind of doing Ohm's law the opposite way that we just did. We know that VNP is equal to I2 times R2. So that leaves us with I2 R2 over R1 plus R2 over R2. And we're trying to solve for I2, so that means we have to flip everything over to the other side. So we'll do this. And that will leave us with IS times. And now what we have is 1 over R2 over R1. And this right here simplified down to 1. Plus 1. And then now what we could do to get this in the right form is we can multiply by a value over itself in order to get this in the proper form. So what we're going to do is we're going to multiply by R1 over R1. Okay, because that will get rid of the denominator inside of the denominator. We normally don't want to have that. The nested denominator. And then if we do that, we're going to end up with the expression that we're looking for, which is I2 I2 is equal to R1 over R1 plus R2 times X. So take away from that what you will, whether it's proof that I didn't just pull that equation out of nowhere, and it's not completely made up, or a good demonstration of how you can make equations with the form that you want. Because some of the homework problems I think do ask you to do that, where they tell you, it may be later on in the book, where they tell you the form of the equation that they want you to get, and they say, take this circuit and make it look like that. All right. So let's take a look at example 2.17. So this is the first one where we're going to have a circuit that's neither going to be a single loop or a single notator. And so the circuit looks like this. Just trying to be careful to draw it the right way. This is all right. So we got a circuit that looks like this. This is either a single node or a single loop or single node. So the first step that I would say here, after label everything, so I'll put that first. So the second step is we ask ourselves, what's our strategy for solving this? So we have several tools at our disposal, okay? We have our KVLs, we have our KCLs, we have our Ohm's law. We have our voltage divider, we have our current divider. We can get into any one of those forms, we have equations that we can solve pretty easily, or that we can solve for. We also have Televin's theorem, right? So if you figure out a way to calculate all the powers. And then we have the combination of the parallel and series elements. So let's assume first that our goal is just to come up with VO. What would you need? So we can't, I can tell you right now, we can't solve this the way that it is necessarily. Because we're not going to know the current flowing here, right? We'll know the current flowing right here, but we won't know the current flowing right here. There's actually a really easy way to solve this without having, because we're going to end up doing the simplification method. But there's a really easy way to solve this if you take a look at exactly what's going on. So we'll do that way second. So if we know the current here what does that mean? And let me do the label, I think that might help me. I'm going to call this the 60. Call this the 40. And that's already defined. That's IS. And we'll call this 60 I 40 and then Okay, well if no one sees it, we'll come back to that at the end. So what we're going to end up doing, I was trying to lead you that very direction. What we're going to end up doing is combining these two series resistors together, okay? The reason why they are series, and you're going to say, well, but there's this thing right here. This current is equal to 0. So that means that these two are still in series. If there was a load over here, then it would be different. So we're going to combine these two together, and then we'll have two elements that are in parallel. We'll combine them together in parallel. We can find the voltage across them, and then we'll have to expand the whole thing back out. So without writing too much here, what I'm going to say is, you know, step one is going to be simplified down to solve for the voltage across the current source. Then expand back out. And when I say expand, that's really going to be using a combination of voltage and current dividers. To regain our resolution. And find the values that are no longer included. Okay, so let's start with our simplification. I'm sorry, I had to move the circuit off. Now, it may seem tedious to keep redrawing these pictures every time. It is. But for better or for worse, it's the best way to keep everything straight at this point, at least. And you might have to be a little bit creative with how you're going to want to label each one of these figures. So you have to be a little bit creative in how you kind of do that. So what does the circuit look like when we combine those two together? All right, we still have our 60 ohm, a 60 kilo ohm. But now what we have is something that looks like this. So let's try to put these two together. So what we've done is, right, we've combined these two together into this. So this is still IS equals 0.9 milliamps. This right here is still going to be what we called before V60. And this right here is still going to be what we called I60 before. This right here is not going to be V out. It's not going to be V40. This voltage here if we were to draw it, is actually going to be, right, the combo of V40 plus V out. Does everyone see why that is? Because the voltage is from this point here to this point down here. And so actually it might help if we labeled the nodes, because then it'll give us an idea of what nodes we still have and what nodes we've lost. So I'm going to call this node 1, I'm going to call this node 2, and I'm going to call this down here node 3. So using that, this is still node 1, and this is down here node 3, but we've lost node number 2. And so this is going to be the parallel combo of 40K and, series. So this is going to be 120K. All right, what's going to be the, why did I write parallel here? In series. Okay, then what's the next step after that? We can also label the current. So what is this current right here? So it turns out that I-40 and I-80, because there's no current flowing this direction, were always the same value. So we can call this I-40 is equal to I-80, same. All right, now let's do a parallel combo. But I would ask, do we need to combine these two together? Do we have a way of solving for this current without combining the two together? Because, right, look at what values are known and what values are unknown. We're ultimately, we're trying to expand back out. So if we can find this voltage right here, we'll be in good shape. This is a type of circuit that we've seen before. What is it? Say again? It is, yes, that's true. But being more specific than that, it is a current divider. And so what that means is we can find the current without simplifying any further. So what I'm going to do is I'm going to say step number 4 is going to be solve for I-40 using current divider. Now you could, if you want to, you could combine these two in parallel. Then you would get the voltage across them, and then et cetera, and move your way back out. But that would just be an extra step that we don't need to do. So I-40, which is equal to the I-80 that we defined, is equal to 0.9 milliamps times, and what's the what goes there? So if we were drawing our generic current divider, this would be our R1 and this would be our R2.
So, so that equations to 60K
Mhm.
over 60K plus 100K.
Exactly. And so what that's going to give us is a 1/3, right? And so what we end up with is 0.3 milliamps. Okay, So now what we can do is we can solve right, we can solve for that using Ohm's law. Or actually, scratch that. Well, no, we do have to solve for. We have to do that first. So. Above. Okay, so let's solve for that. We know that V40 plus V out will be equal to what? So it'll be equal to, using Ohm's law, so that'll be I40 times 120K. So that'll be 0.3 milliamps times 120 kilo ohms. And so that gives us, we'll wait a couple minutes here. So 0.0003 times 120, so that's 36 volts. And then now we can expand circuit back out. So let's draw our original circuit. We go back and look at this right here. So we now know the voltage right here, which is V40 plus VO. Right? You can see that this is another type of circuit that we're used to seeing. What circuit is that? So if we imagine we know V40 plus VO plus minus, we know that this is going to be your 40K. This is going to be your 80K. And this is your V out. Right? So that is a voltage divider. And so I'm doing this a little bit quickly here at the end. So we know that V out will be equal to 80K over 120K times our 36 volts, which gives us, so what is 80 over 120? That's 3/4. So what is 3/4 of 36? 36 divided by 4 is 9, right? So 27. And so hopefully that's the answer that we got here. And then we're done. Yeah. All right. So, you know, these types of problems, it takes homework in order to get used to it. Because as much as we set a strategy at the beginning, it's sort of like, okay, well, why do you do this next thing? Why do you do this next thing? You just have to get the hang of it for that. It's kind of like trying to explain to someone how do you run a car. You just learn how to don't forget the quiz today. If you have any questions during the interim, feel free to email me. Quiz starts at 5 on night. And have a good weekend. See you guys on Monday. Because there's no current flowing. You look